Let's start by adding a new method. Public, we're going to return a weighted graph, and we call our method getMinimumSpanningTree. Always use descriptive names for your methods. Now here we need to create a weighted graph object. So weighted graph, we call it tree or minimum spanning tree. I'm going to go with the name tree because it's shorter, and it's obvious that here we're creating a minimum spanning tree. So there is no need to come up with a long variable name like minimum spanning tree. That's way too long. So let's just call this tree. We set it to a new weighted graph. We can simplify this code. We have repeated weighted graph twice, so we can replace this with var. That's better. Now we need a priority queue. So priority queue, we're going to use the one in the java.util package, not the one we created earlier. So let's use this. And in this queue, we're going to have a bunch of edges because we want to find the minimum weight edge, right? So let's call this edges and set it to a new priority queue. Now, earlier I told you that here we need to pass a comparator object in the constructor. So the priority queue can figure out how to order these edges. We're going to order them based on their weight. So edges with a smaller weight should appear at the front of the queue. So here we're going to use the comparator interface. We call this factory method comparing int. This will return a comparator object for comparing two integers. Now in this method, we should pass a function using a shorthand syntax. So this function should take an edge and return the weight of that edge. This comparator object then will compare the edge objects based on their weight. Okay. Again, if this is confusing, don't worry. I'm going to cover this in detail in my upcoming Advanced Java course. So here we have our priority queue. Now we need to pick a node from our graph and add all of its edges to this priority queue. That's our starting point. So let's pick a node. We go to the nodes hash table. We get the values. Now here we can convert this to an array and pick the first item, but I showed you a better way. So here we call the iterator method. This will return an iterator object. We can use that to read one item from this collection. So we call the next method, and this will return a node object. Let's call that start node. Now we need to add the edges of this node to our priority queue. So edges, then add all. We can add a bunch of edges together. Here we call start node and then call the getEdges method. This is better than doing a for each loop and adding one edge at a time. It's just cleaner. Now we should also add this start node to our spanning tree. So every time we discover a node, we add it to our tree. Okay. So here we call tree.add node. We should pass a string here. So start node.label. Now, what is interesting here is that these nodes are completely different. We are not working with the same node object in memory. So start node is the node in our graph. We pass the label of this node to our tree, and our tree will internally create another node with the same label and store it in memory. So all the nodes and edges in our tree are going to be different from the nodes and edges in our graph. Okay? Now, we're done with the initialization. Now we should repeat. So as long as our tree doesn't have all the nodes in our graph, we should repeat. So here we need a while loop. While tree.nodes.size is less than the nodes that we have in this graph, we're going to repeat. In every iteration, we're going to remove the minimum edge weight from our queue. So edges.remove, this will return the minimum edge. Now we should check to see if we have visited the target of this edge. If we have visited that node, we should get another edge from our queue. Okay. So if tree.nodes.contains key minimum edge.to, that is our target node. Now here we should pass a string. Because this contains key method is part of our hash table, it takes a string and tells us if we have an entry with this key in our hash table. So if this condition is true, then we're going to continue. Now, I don't quite like this code. It's a little bit too lengthy. I would prefer to create a new method in our graph called contains node. Just like we have add node, we're going to have contains node. So this is the end of our method. Now, here in the weighted graph class, let's add a new method. Public boolean contains node, takes a string. And here we return nodes that contains key label. With this method, we can replace this code with something shorter and more expressive. So if this tree contains this node, then we're going to continue. By the way, I made this public because it's a useful method to have in a graph. So from the outside, we can call graph. Here we have add node, we have contains node. Potentially in the future, we can have remove node and so on, okay? Now, back to our while loop. If we have visited the target node, then we're going to continue. Otherwise, we should add this node to our tree. So tree, then add node, min edge, the to, the label. Now, I don't like that we have repeated this expression twice. I would prefer to extract this in a local variable. Let's call it next node and set it to min edge, the to. Okay. Now, we can make this code even better. So we replace this with next node. And one more time here. So we're adding the next node to our tree. We should also add this edge to our tree. So tree, then add edge. Here we pass min edge, dot from the label. Next, we should pass the label of the next node. And finally, the weight of this edge. Now let me put this on a new line. That's better. So we add this edge and the target node to our tree. Next, we need to add all the edges connected to this next node to our priority queue. So in the next iteration, we can look at all the connected edges and pick the one with the minimum weight. So here we do a for each loop. For each edge, a next node that get edges. Now, if our tree doesn't contain the target node, then we're going to add the edge to our priority queue. In other words, if you have visited the target node, we're not interested in this edge. So if our tree doesn't contain this node, that is edge, the to, the label, then we're going to add this edge to our priority queue. So edges that add edge. Okay? So let's quickly recap. As long as our tree doesn't contain all the nodes of our graph, in every iteration, we're going to pick the edge with the minimum weight from our queue. Then we check to see if this edge is connected to a node that currently exists in our tree. If that's true, then we're going to pick another edge, okay? Otherwise, we're going to add this edge and the target node to our tree. And then we're going to add all the edges connected to the target node to our priority queue. But we're only interested in the edges that connect us to a node that we haven't visited so far, okay? Now, after this while loop, our tree is complete, so we can return it over here. Now let's test our implementation. So here in the main class, I have created the graph that we had in the previous video. Now let's call graph that get minimum spanning tree. We store the result over here, and then we can print it. Now, if you compare the result with the minimum spanning tree that we came up with in the last video, you can see they're identical. Now, what if our graph doesn't have any edges? We got an exception, no such element exception. So let's see what's going on here. So in our while loop, when we're trying to get the minimum edge, we get this exception. So to handle this, before this while loop, we need an if statement. If our queue is empty, we're simply going to return our empty tree. Let's run the program one more time. Beautiful. What if our graph doesn't have any nodes? Let's see if our code works. As I told you before, we should always test these edge cases. Now, there are times that I probably forgot to do that in the videos, but you got the point. So here we have another exception, no such element exception. We got that exception on this line when we're trying to add the first node to our tree. So right at the beginning, before we even create this priority queue, we check to see if we don't have any nodes in this graph. So if the nodes hash table is empty, we're going to return this blank tree. Let's try it one more time. There you go. So this is the proper way to implement the Prim's algorithm. Now, if you look at the other implementations online, you can see their code is disgusting, literally disgusting. Honestly, when I was reviewing this algorithm and its implementation, because I studied this long time ago, almost 20 years ago back at school. So I had to review it and look at various implementations to refresh my memory. I looked at these implementations and honestly, I just wanted to throw up looking at the code written by these so-called computer scientists. Your code should always be clean and expressive, so others can read it like a story. This is what differentiates you from the average programmer out there. Throughout the course, I've tried to show you numerous ways to refactor your code and make it cleaner and more expressive, and I hope you have learned a lot. So that brings us to the end of this course. I want to congratulate you for all your effort and finishing the course, and I hope to see you again in my other courses. If you enjoyed this course, please tell others about it. I really appreciate your support. With your support, I can create more courses like this for you and other people around the world. So thank you and have a fantastic day.